Hey, scholars, welcome to the last lecture uh, for Chapter 8. Okay, so after this, you'll get to the lab for Chapter 8, and then for Chapter 9, we'll pick up hypothesis testing for two samples. Okay, all right, so let's go ahead and get going here. All right, so the objectives are largely the same as the previous sections. Same thing here with the key terms. All right, not a whole lot of difference there. All right. Um, all right, but just to kind of remind ourselves of kind of where we are and what's going to be the focus of this of part three. Right? So the first part, we just introduce some basic concepts. What's a hypothesis? What's the purpose of hypothesis testing, and so on. Okay. Part two, we got into some more of the conceptual content. The null hypothesis, alternative, alpha, power analysis. All right. So here's where we get into the methodology of the test. Okay, of the hypothesis test, the T-test specifically. All right. So we're going to review the equation, talk about testing assumptions or the assumptions of the t-test, and then conducting the t-test using SAS. So again, you'll see a lot of equations, but well, not a whole bunch, but you'll see some equations. Um, but you want to remember that you're going to tell SAS to do all this stuff for you. It's going to do all the computations for you. Okay. All right. Let's see. One of the biggest points you want to kind of take away, and this is going to be something that's going to be crucial for your advanced courses, at least the ones where you're working with a lot of data, um, uh, interpreting results. Okay. So you want to be able to take a look at SAS output. All right. And what you're going to, what happens, folks, with these statistical programs, when they run analyses, they run many different analyses. So if you just ask for a t-test, all right, well, there's certain things that it also has to do to give you enough information to know what's going on. All right, so you can fully critique your results. Okay. All right. However, for the purposes of this class, you only need like a few things. All right, so you're going to see SAS is going to spit a lot of stuff at you, but there are only a few things that you need from all these tables and all these numbers you're going to see in the output. Okay, and that's what you want to keep in mind. You want to be able to find those numbers, and then you want to be able to interpret those numbers. What do they mean for your hypothesis? Is your hypothesis pass the test or did it fail it? Okay. Um, you just keep that in mind, okay? Keep that in mind. All right. All right, and then we'll talk about well, like we just said, making a decision about the null, that our hypothesis, the null hypothesis, um, was the null hypothesis confirmed, or was can it be rejected? All right, and then again we'll get into some examples using SAS. Although I saved most of that for the lab. Okay. All right, let's go. All right, so again, just as we talked about testing assumptions, conducting the hypothesis test, looking at the t-score and degrees of freedom, and then making a decision about the null, that's going to be our emphasis. All right. All right, so when we get into testing assumptions, again, folks, this is really, really important stuff, okay? Because what uh, you want to keep in mind that um, these hypothesis tests are designed for specific situations, much like uh, a lot of the equations you're first exposed to in mathematics, right? So the area of a circle, right, uh, is the equation for the area of a circle assumes you're working with a circle, and in many cases, what they call a unit circle. All right, so that means it's perfectly circular. Okay, it's not sort of oblong in some sort of way. All right, there's no skewness in it. It's a perfect circle. All right, but if you apply that to maybe a square, all right, well, you'll get a result, but the result would be incorrect, right? And it's only incorrect because you misapplied the equation, all right? So you don't want to misapply a test, right? So you don't want to apply a test in conditions that it's not built to handle, right? All right, so there are, when we talk about hypothesis tests generally, all right, well, there are kind of these four assumptions here. It assumes that your data comes from a random sample, all right? We could even say data come from a random sample of a well-defined population, all right, because that would also be important, all right? But, you want to make sure it's a random sample. Variables are measured at the appropriate level. So, you want to make sure that your statistical test, whatever test you're using, can handle nominal variables and/or ordinal variables and/or interval variables and/or ratio variables. Okay. All right. And then also the exact shape of the sampling distribution is known. So in the case of the t-test, the sampling distribution is assumed to be a normal distribution. Okay, and as we demonstrated, I think was that the second part, chapter 8, part 2, or perhaps even before then, as we demonstrated, okay, if we take a random sample and then we construct a sampling distribution, is not perfectly normal, but it's approximately normal. Okay, so at least it approaches the ideal shape. Okay. All right, and observations are independent. So what that means is that, let's say you are working with a sample of just 3 people. All right, well, let's make it even simpler. You're working with a sample of just 2 people. All right, the observations are independent to the degree that the responses that one person in your sample gives you are not influenced by the responses of another person in the sample. Okay? All right. So in that case, you would say that the observations that you get from the first person are independent from the observations you get from the second person and vice versa. Okay? All right. But if you have a situation where the observations from one person influence the observations that you get from a second person, all right, the t-test doesn't apply. All right, that's one of the crucial assumptions that needs to be met for the t-test. Right, the observations are independent, and that's independent observations. That's kind of important for a lot of different tests. Okay. Not all, but for a lot of them. Okay. All right. So for the t-test specifically, all right, so the 4 we just covered are for test in general, right? But for the t-test specifically, right, data come from a random sample. The variable is interval or ratio, right? And the variable has a normal distribution in the population. All right. Now, having said all of this about the importance of your test conditions meeting the test assumptions, right? One thing we do want to keep in mind is that even if the assumptions are not perfectly met, okay, the t-test can still give you a reliable result. And in that case, we would say that the t-test gives you robust results, okay? So even though your data doesn't meet the assumptions of the test perfectly, right? Maybe they get kind of close, or maybe one or two of the assumptions your data just, doesn't quite meet at all, right? The t-test can still give you some reliable results, okay? Reliable meaning, again, that even though your results might not be exactly what would be found if you were working with data from the entire population, you would still be in the ballpark of what you would see out there in reality, okay? You would still, well, let's say just not, let's make it even, a little more precise. Let's say that you'll be within the baseball diamond, right? Of having results that do reflect reality, okay? All right. So one of the ways you can test the assumptions about the variable's distribution, again, this for the t-test, it assumes your variable is taking on a normal distribution. All right. One of the ways to just simply conduct a simple test is to run a Proc Univariate. Okay, you can just set up something like this, very simply like this. So Proc Univariate, data equal, and then whatever data set name you have there. You indicate the variable. So here is just a generic X for the name of the variable. All right, and then you want to make sure you put in these options, histogram / normal, okay? Because if you have those in there, SAS will run a full check of your data, right? And you'll be able to assess whether or not your data meets at least some of the assumptions of the t-test, okay? All right, let's see. All right. So when you run that Proc Univariate statement, SAS will give you 3 different tests, right? And these tests are designed to kind of see how well your sample data fits a normal distribution, okay? So we have the Kolmogorov-Smirnov test, the Kramer-von Mises test, and the Anderson-Darling test, okay? Now, the one that tends to be used most widely is the one that's in bold there, the Kolmogorov-Smirnov test. And so we'll talk about that one. But, in some of your other classes that you get into, you might talk about the other 2, all right? But all of them essentially do the same thing. They take a look at your data, they look at the distribution of your data, all right? And then they compare that distribution to a perfect normal curve, all right? And the results of the test essentially tell you how far, well, it tells you 2 things. It tells you how far or how closely your data comes to a perfect normal distribution. And then it also tells you the probability of your data coming from a normal distribution. Okay. All right. Or rather, it essentially tells you the probability of your data coming from a normal distribution. Okay. All right. So all 3 tests are hypothesis tests. All right. All right. So for the null hypothesis, CDF, cumulative distribution function of your variable, of var1, all right, is equal to the cumulative distribution function of var2. So var2 With these tests, you don't have to compare it to a perfect normal distribution. You can compare it just simply to another distribution of a different shape, so on. Okay? All right? But typically, when the Kolmogorov-Smirnov test is used, right, your data is being compared to a perfect normal distribution, and that's what's going to happen here. And that's what you're going to do for the lab, and that's also what you're going to do for the last gear project. Okay. All right. Okay. All right. So again, like I was saying, the Kolmogorov-Smirnov test, or the KS test, gives you these two results. So it gives you the difference between your variables, cumulative distribution, and the cumulative distribution of a variable with a normal distribution. Okay. All right. That value, D, ranges from 0 to 1. Right? And what you want to keep in mind is that a value that approaches 1, or a value that is equal to 1, all right, indicates that your variable closely fits, or is an exact fit to a perfect normal distribution. All right. And then the PR greater than D, all right, value also ranges from 0 to 1. All right. And again, this tells you the probability. All right, so technically it tells you the probability of the null hypothesis being true. Now, your null hypothesis, all right, is essentially saying that your data fits a normal distribution. Okay? All right? So typically what happens is that if that value, if the PR, D value is 0.05 or something lower, all right, that means that the null hypothesis has only a very small probability of being true, right? Or, if you want to put it in the terms of chance, it only has like a 5% chance of being true. All right, well, that's no good. All right, typically we want something that's larger than that if all right, if we are hoping that our data conforms to a normal distribution. Okay. All right. So again, we'll go through all this. We'll show you what the SAS output looks like, and we'll highlight where you get the value of D and where you get PR of D. All right. We'll tell you exactly where to find that information in the SAS output. Okay. All right. Because again, it's going to look like a lot of output that SAS gives you back. Right. But if you know exactly where to find the two values that you need, all right, well, that makes it a lot easier to get through it. Okay. All right. So as I said, right here. So the Proc Univariate output, this is only a very small piece of it right here, where you have the table that reads goodness of fit test for normal distribution. Okay, this is only a very small piece of what you get out of that Proc Univariate output. Okay, all right, but again, we're looking at the Kolmogorov-Smirnov test, and we want to take note of the value of D, which is right here under statistic, right? The value of D. All right, so here we say we see that it's 0.016, or we'll say 0.02. All right, and that's pretty close to 0, right? That's pretty close to 0, given that you have essentially 0.98 points above that as a possibility. Okay, all right, and then we take a look at PR greater than D. All right, so here we have a value of 0.15, which is larger than 0.05. All right, so in this case, what it's saying is that, well, the data that was compared to a perfect normal curve matches up with it pretty well. pretty closely, right? Because again, if D is 0, it's a perfect fit, okay? All right, so we have something that looks pretty close to a perfect fit, all right? Which means that, well, we can't reject the null hypothesis, right? Because again, if the null hypothesis is 0.0, or if the PR of D value is 0.05 or less, right, then that means that there's only a very small probability of the null being true, therefore we reject the null. All right? But in this case, we have a PR of D value of 0.15, so that's quite a bit larger than 0.05. So in this case, we say that there's a pretty good chance that the null is true, okay? Meaning, in this case, that the sample data that we compared to a perfect normal curve matches up pretty well with a perfect normal curve. It comes pretty close to it, all right? All right, so again, all this is to test the assumption that your data comes from a normal distribution, okay? All right. All right, here's some of the other output that you'll get from the Proc Univariate. So the table is the most important stuff, but to kind of help you visualize what's going on, you can, if you run that program in SAS exactly the way I wrote it, you'll get some nice visual graphics like this. So it'll show you the distribution of the variable, right, that's being tested. And then it'll plot a normal curve against that. So we can see from here that our distribution, represented by the bars, if it was a perfect normal distribution, everything would be on the inside of this curve, this normal curve, right, and touching the curve, right? Everything would be on the inside and touching it, right? But you see that some of it, a little bit of it is on the outside of the curve, right? But the vast majority of it is inside the curve. All right, so it's not a perfect, our data is not a perfect fit, which is usually the case, as a matter of fact, if one of you were to say that, oh, look, Dr. Davis, I tested the assumptions of my data and it was a perfect fit, I just wouldn't even believe that you did it correctly. Nothing is perfect, all right? Especially if there's some chance of random error, okay? It's not going to be perfect. All right, but anyway. And believe it or not, folks, there have been PhD scientists, who wanted to try to make a name for themselves, who fudged their data and got caught later. They still have their PhD, but they can't find the job anywhere close to a university, right? They would be lucky to get a job, mopping the floor at a, shit factory, right? But anyway, I harp on that because I cannot believe some of these folks would try to get away with that. These are PhD scientists trying to get away with shit like that, right? And they're at some of the most prestigious universities in the world. But, they're trying to make a name for themselves and they tried to take shortcuts to getting there, all right? So don't do that. All right, so we have this one graph here, right? And then we have the graph that's actually generated by the Kolmogorov-Smirnov test, all right? So here, again, remember, the Kolmogorov-Smirnov test quite literally matches your sample, the cumulative distribution in your sample to the cumulative distribution of a normal curve, all right? So there are actually two lines that you're looking at here, okay? There's one very smooth line that's kind of hard to see, right? There's one very smooth line, and that smooth line represents the perfect normal curve. curve, perfect normal distribution. Okay. All right. And then there's a jagged line. Okay. And you can kind of make that out a little bit. All right. And that represents your distribution. All right. And so these little jagged points correspond to these areas where your sample distribution kind of falls outside that perfect normal curve, right? So where it does that, that's where you start kind of seeing those jagged points over here. Okay. All right. So what you have going on over here, I have here, the lines overlap almost completely. And when you have that case, all right, this is, again, visual confirmation that your data looks very much like a normal curve, a perfect normal curve. It comes very close to that. It's not perfect, right? Because then, if that was the case, you'd see, both the line representing the perfect normal curve and the line representing your sample data. There you would see they would be perfectly overlapped, and you would essentially see just one line here, one very smooth line. Okay. All right. So here, so you have the numerical information in the table on the previous slide to, show you the results of the test, to show you how well your data matches up to a perfect normal curve. And then you have the visual confirmation as well. All right. All right. Now, for the first example, so for the first, the last couple of slides, that was showing you what the results for a Kolmogorov-Smirnov test looked like if you have sample data that comes from a normal distribution. Okay. Here, we're going to take a look at sample data that comes from a non-normal distribution, just to kind of give you a feel for how different the output for a Proc Univariate would look. All right, how different the output for a Kolmogorov-Smirnov test would look. All right, so here, this is for again, a sample where the data is a very poor fit to a perfect normal curve. So the Kolmogorov-Smirnov test is 0.24. Okay. So that puts quite a bit of distance between what a perfect normal curve looks like and what your data looks like. Okay. All right. The PR of D. Okay. Well, it's considerably less than a value of 0.05. And remember, if it's 0.05 or less, right, then you reject the null. So you say that, well, chances are the null is not true. So in this case, there's only a 1% chance of the null being true, according to our calculations. There's only a 1% chance of it being true. All right. So then we have to reject the null hypothesis. So again, remember what the null hypothesis for the Kolmogorov-Smirnov test states, right? It says that your sample data is exactly equal to the data, or the shape of your sample data is the exact shape of a perfect normal distribution. All right. So the CDF of your variable is exactly equal to the CDF of a variable that represents a perfect normal distribution. Okay. All right. So, but in this case, again, since we have only a 1% chance of the null being true, we say, all right, that statement that our sample data is exactly equal to, or looks exactly like data that comes from a perfect normal distribution, is probably wrong. We say that statement is probably incorrect. So we reject that statement, all right, as true. All right. All right. So let's take a look at this. Let's compare visually the shape of the distribution for this sample to a perfect normal distribution. All right, so you get something that looks a whole lot different, right? Okay, so here we can clearly see that this variable is not normally distributed. Okay, and again, you know, the perfect normal distribution is it's a horrible fit. Okay, our sample data is a horrible fit to this perfect normal distribution. Okay, all right, and that's plainly obvious. All right, same thing here. All right, so the smooth line represents the perfect normal distribution. So again, right, the more jagged line represents our sample. All right, so we see these wide gaps between what our sample CDF looks like and the perfect normal distribution CDF looks like. All right, some pretty wide gaps. Okay, or as we might say, significant deviation or separation between those two curves. All right. All right. So again, we have numerical evidence, and now we have visual confirmation that the sample that we're using for this example is not a good fit. Okay. It's not a good fit to a normal distribution. All right. So what does that mean? It means that you might want to find a different test. Okay. So don't use the t-test in this case. Don't use the t-test. Use a different test. All right. All right. And again, folks, you know, when you get into your upper level classes in statistics and research methods, right, you'll be taught other tests that are out there that could, you know, test a variable with this sort of distribution. Okay. All right. Let's move on. All right. So the t-test itself, we covered this equation a little bit. All right. Um, in the previous lectures. Okay. For chapter 8. All right. So here, you know, here we just want to kind of, you know, make sure you understand what's going on. All right. Because in place of these terms like sample, statistic, null value, and things like that, you'll see symbols. Okay. All right. So this test essentially does these things. All right. So first it compares your sample statistic, well, whatever that is, whether it's a mean or a proportion. It compares that to a null value. All right, and again, we talked about how you develop a null value. Okay, and again, this is the expected value if your sample statistic was determined completely by chance, right? So the null value in this case, again, it can represent other conditions. But in this case, and for this class, right, that null value is always going to be the value that represents what your sample statistic would be if it was completely determined by random error, okay, by random sampling error, okay. All right. So then, what this equation does, it essentially converts it converts this difference between your sample statistic and the null value to a t-score, okay? And then it takes that value for t, all right? It takes the t-score for this comparison, and then it essentially plots it in a t-distribution that represents sampling error, okay? All right? And then from there, it says, okay, given the t-score that's computed for this comparison, right, in a distribution of random sampling error, this is the probability of that t-score occurring in that distribution, okay? All right, and we'll talk about how it adjusts for degrees of freedom. But very quickly, just remember that the more degrees of freedom, the better your test is. Uh, and, the fewer degrees of freedom, the harder the test is to pass. Okay? Because again, it penalizes you for using a bunch of information to make the prediction, essentially. Okay? Right? All right. All right. So the hypothesis for the t-test look like this. This is for the single sample case, right? Where the mean, in the case of the mean, right? The mean from your sample is equal to the expected mean under the null condition. The alternative hypothesis states, right? The mean is not equal to the null. Same, roughly the same thing here for the proportion. Oops. All right. That's supposed to be HA right there. Sorry. Right? That HO is supposed to be HA. All right. All right. So in the so for the null hypothesis, right? The proportion from your sample is equal to the proportion that would be expected under the null condition, right? And again, this is for the alternative, so that's supposed to be A, H sub A, right? That would read the proportion from your sample is not equal to the proportion that's observed in the null condition. All right, so again, you want to use the not equal sign because that gives you a stronger test. In other words, your data has to perform at a higher level in order for you to be able to reject the null hypothesis. Okay. All right. So you always want to just use the not equal sign for your alternative hypothesis. Okay. And again, I apologize for that. I don't know how that got by me. Okay. I'll put a little note in here to just kind of remind you. All right. All right. So again, conducting the t-test, when you're working with a single sample case, you could again just use the Proc Univariate procedure, right? The univariate procedure to conduct for the single sample case. So this wouldn't work when we get into chapter 9 and we look at the two sample t-test. The two sample t-test. Sorry about that. When we look at the two sample t-test, the Proc Univariate approach won't work for that. It does work for the single sample t-test, as we'll show you in just a second here. Okay. All right. So like I was saying, when you run this, you're going to get a whole bunch of numbers spit at you. You have your statistical moments, the sample size, the means and all of that sort of stuff, right? So you got a lot of stuff that's thrown at you, okay? All right, but they're really just kind of a couple of things you need, right? And they're all in this table, right? And to be even more specific, right, it's all right here on this first line, okay? All right, under test for location, you just want to take a look at the student's t-test. All right, so that is the t-test that you're looking for. All right, so that's the t-test you'll be looking for, or this is the line that you'll be looking for when you get to the quiz for chapter 8, and you have to, sort through some output from SAS. Okay. All right, so you just want to go right to this line. All right, so the first value, the value of t that you have here, essentially says that the mean that's observed in the sample of 1,000, all right, and again, this is for a normally distributed variable, all right? The t that's observed here is 31,410 standard errors from the mean that would be expected for the null condition, all right, under the null condition, okay? All right. So that's a huge difference. All right. That's a huge difference. Right? Typically, you can reject the null when it reaches a value of, when t reaches a value of, 2 or greater. All right. Sometimes you can, say, all right, well, yeah, that's a pretty large difference when it's just 2 standard errors from when the mean of your data or the proportion for your data falls 2 standard deviations away from the mean in the distribution of the null. Okay. All right. Here it's 31,410 points, or standard errors, away from the mean or the proportion that would be expected under the null condition. All right, so it's way far away, way different from what we would expect if we were looking at a distribution that was completely determined by random error. Okay. All right, and so as the PR of t, right, the absolute value of t, so as the PR of t indicates here, right, the p-value is less than 0.05, right? Way, way, way less than 0.05. All right, and this is not even the exact value. SAS is just saying that the value is really, really small, right? And it's even smaller than 0.0001, okay? So it's way, way smaller than a 0.01% chance, okay? All right? So there's a very, 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 very small chance of your data occurring in a distribution that represents random error, okay? Really, really small chance, okay? All right, and I think, yeah, I got something of a visual here. All right, so like I was saying, in a lot of distributions that, sometimes, if your data falls right about here or, over here, right, that is far enough from the mean or from the center of that distribution, whatever it represents, right? That's far enough away to say, well, no, the null is, our data doesn't look like it would come from a distribution of random error, okay? It doesn't look like that at all, all right? That's at 2. At 5, right, so if we were looking at, positive 5 or negative 5, we would see that the chances of the null being true would be 0.0002%, right? So again, super, super small, all right? But what we observed in the table in the previous slide, right, is 31,000, right? Right? T is 31,410 point, some change, all right? So it would be way, 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 way out here, okay? It would be way out here, all right? And so that gives you some, really, like, way out here and, even going further off the page, right? All right, there's no way we could fit 31,000 onto this slide. All right. Okay, so at t equal 31,410, all right, a super small, all right. And when it gets out to that point, remember the t distribution, right, is asymptotic, all right. So you never get to a point where the probability of your sample data occurring in a null distribution becomes 0. All right, you never get to that point. There's always some non-zero chance of your data occurring in a distribution of random error. All right, there's always some non-zero chance. Okay, but after it gets way, way far out there, like we see here, 31,000 standard errors out from the mean, right? Once it gets way, way out there, we can kind of treat it as zero. We can say, all right, well, yeah, there's probably a 0% chance. Okay, all right. I mean, technically it's not zero, but it gets so close to zero, you could say, all right, well, we can safely treat that as zero. Okay. All right. Now, here's what it looks like. Oh, I'm sorry. I thought we were going to a different variable, but we're still with the same variable. So we're coming back to the table that we were. All right. So when we're thinking about making a decision about the null, so remember the two options that we have for our decision is that, well, we either reject the null or we fail to reject the null. Or some people would say, if we reject the null, instead of saying reject the null, they'd say accept the alternative hypothesis. All right. But again, I don't like saying accept the alternative hypothesis because, again, it's not the alternative hypothesis that's being tested. Okay. It's only the null hypothesis that's being tested. All right. All right. So anyway, so our options here for our decision, do we reject the null, or do we fail to reject the null? All right. So again, when we take a look at the PR of t value, all right, we see that it's less than 0.05. All right, way, way less than 0.05. All right. So if that's the case, we can say, all right, well, we can say that the null has an extremely small probability of being true. So we'll just go ahead and reject it as false. All right. So we'll say that we can reject the null. All right. And again, what does that mean? What does that mean for your data? All right. If you reject the null, at least in the context of this example, all right, when you reject the null, this means our sample mean is highly unlikely to be the result of random sampling error. It's highly unlikely. All right. So notice that even though we can go ahead and say, it's, in actuality, maybe our value of p is so close to zero, we can pretty much go ahead and treat the null as having 0 chance, right? But since there's always a non-zero probability of the null being true, we just say, all right, it's highly unlikely that the null is true. Okay, it's highly unlikely, right? So we don't want to say it's not at all likely. We'll just say, it's probably false. Okay. All right. Now, here's the second way to run the t-test, right? Just to use what's called Proc Ttest, the t-test procedure in SAS. And again, you see it's really not that difficult. Okay. All right. So you call it up, Proc Ttest, all right? Give it, give SAS some data to use, right? And these are options, and you don't necessarily need to include all of them. For the single sample t-test case, you want to make sure you include a null value. All right. You'll see that in the two sample t-test case, the null is always 0, right? So regardless of what the means are that you're comparing or the proportions are that you're comparing, the null is always going to be 0. And we'll talk about that when we get into chapter 9. Okay? But anyway, alpha, we can go ahead and set that to 0.05. Right? So remember, this alpha is setting the difficulty of the test. So in order to pass this test, the null hypothesis can only have a 5% chance of being true. Anything above that, and we'll say that we fail to reject the null hypothesis, or we accept the null hypothesis. Okay, that's true. Cited, so here we're saying that we want SAS to run a two-tailed test of significance. All right, you can, if you don't include this option, cited equal to, SAS will by default use a two-tailed test. Again, because that's the strongest test of your hypothesis. Okay, all right, it's the strongest test of your hypothesis. All right. And then we take a look, we tell SAS what variable we want it to use from our data, okay? And we go from there. All right, so a little less information to take a look at when you use Proc Ttest. It sort of goes right to the point a little bit more. All right, but in this case, you're looking at this table, all right? All right, all this is useful information up here, but to simply make a decision about the null hypothesis, you just need this information right here. Okay, and since we're using the same variable we use in the Proc Univariate example, we're seeing the same results. All right, so here we have a really small value for the probability of t. Okay, so the probability of your data occurring in a normal distribution that the probability of your data occurring in a distribution that represents random error. Okay. All right. We have this enormous t value, right? 31,410. Okay. All right. And then it also shows you degrees of freedom. So 999. So out of a sample of 1,000. We only use that one parameter, the mean, to run the hypothesis test. All right. And so what we have here, we essentially say, all right, well, we'll fix one value, one observation, all right, at the mean. Okay. And then we'll say all the other observations, 999 observations, are free to take on any value. Okay. They're free to take on any value. All right. And again, you would interpret this the same, right? Since PR of t is, less than is 0.05 or less, or in this case, it's far less than 0.05. We can say, all right, well, we reject the null, and we say that our data probably does not come from. It's highly unlikely that our data comes from a distribution of random error. Okay. All right. What else do we have here? All right. Proc Ttest output. So this essentially does the same thing as the Proc Univariate with the Kolmogorov-Smirnov test and the histogram/normal options. All right. It'll give you the output where it takes your data, takes your sample data, plots it out in a histogram, and then it plots a normal curve against it. And it also plots what's called a kernel distribution, okay? All right, and that kernel distribution kind of fits, it gives a tighter fit to what your data looks like. We haven't really talked about that, so you don't need to worry about it at this point. It's not a very difficult concept. It's just that I want you to focus on just two things: what the histogram of your data looks like, and then what that, how it compares to a perfect normal distribution. Okay. All right. So here again, since we're using the same data we use in the Proc Univariate case, all right, we're seeing the same results here. All right. A slightly different way of checking the fit between what your data looks like and a perfect normal distribution. All right, so here you see all the circles here. All right, and all those represent observations from your data. Okay, each circle, we'll just say each circle represents one person. All right, and you can see there are a whole bunch of people stacked up right in here. Okay, fewer people on the extremes, but a whole bunch of folks stacked up right in here. All right, if you can make it out, there's a nice straight line right beneath that, right? Okay, and if all or most of your observations fall along that straight line, you're looking at something that's very close to a normal curve. Okay. All right. Looks, like you have over here. It looks very much like a normal curve. It's not perfect because you have some of these observations falling off that line. Okay. Right. But most of it, looks like it matches up pretty well, which is what we see over here. Okay. All right. Now, here's where we can just, this is the last slide here. Well, not the last slide, but, we're pretty much done at this point. But you always want to think about what are the practical implications of, the t-test results. All right. So these are some things you want to keep in mind. All right. If you reject the null hypothesis, it means your data probably reflects some aspect of reality. Okay, but only a very narrow slice, right? The slice of reality that you actually tested. Okay. And you don't want to make more of it than that. Okay. And you don't even want to make a very strong statement like, oh, my data absolutely reflects reality. You want to say, well, yeah, there might still be something out there that's biasing our data, something that's acting as some influence of error on our data. All right. So all we can say is that, well, we probably are capturing, this very small slice of reality that we're attempting to understand. But the only way we're going to be absolutely confident in what we see in our results is if other people find, the same or something strongly similar when they, collect data from the same population, using the same measurements that we use and coming up with the same results from their hypothesis test. Okay. All right. So it never means, as I have in the second bullet point, it never means that we have completely captured reality. Okay. All right. And for no other reason that, well, we don't know what that population parameter is. Okay. We still don't know what it is. Everything, all these methods we've been talking about, so like the sampling distribution that we talk about talked about in chapter 7, all of that is so absolutely crucial to telling us, how reliable our data might be, right? All of those things are centered on the expected value, which comes from your sample. It's not coming from it's not based on the population parameter. It's coming from the expected value, which is based on your sample. Okay? And even the sampling distribution that we talked about in this lecture, right? That's based on a distribution of other samples based on your sample. Okay? so we still don't know what that population parameter is. And only in very few cases do we actually know what it is. Okay? All right? So we always want to be careful when we make some sort of statement, some sort of overall statement of what we have in our data, what our test results show. Okay? All right? So all right, so when you're in your classes and you're conducting a t-test or some other hypothesis test, just remember, if you don't know the population parameter, you cannot make any strong statement about your hypothesis. The truth or falsity, well, you certainly can't say anything about the truth of your hypothesis. You can say something about the falsity of it, right? Because if your sample statistic looks exactly like the sample statistic that would be expected in a distribution of random error, all right, then your data's crap, okay? Right? But you'll never be able to say something like, see, the hypothesis test proves that we're capturing reality. You'll never, ever be able to say something that strong. Okay? As long as you don't know what that population parameter is, you'll never be able to say anything that strong. Okay? All right? Okay, so that's it, I think. Yep, that's it. So what we want to do from here, all right, we want to go ahead and jump into the lab, and then we'll get into Chapter 9. And you'll be happy to know that the lecture for Chapter 9 has only one part, and it's short, okay? It's not going to take anywhere near an hour, okay? The gear project that we go through is going to be based on chapters 8 and 9, okay? So you want to make sure you complete the lecture for chapter 9 before you start up the gear project. Let's see. All right, folks, once again, chapters 8 and 9, these are the last chapters we'll cover for the course. Okay? All right, because I think I've given you quite a bit to work with, all right? And I think you'll be quite ready for your upper level classes in statistics. But thinking about that, if you need help in those upper level courses, I'll try to help you out, all right? So, keep my contact information, and I'll try to help you out, all right? Okie doke. Next up, lab.